Hey guys, so in this video we will be adding the concept of complex numbers to our idea of a Hilbert space that we have developed in the last few videos. So the first thing I want to point out are these identities of complex numbers. I've got 7 of them up at the top left. And just to go over them quickly, this first one is the definition of a complex number. We have some complex number z, which is a plus bi, where a and b are real numbers, and then I is the square root of -1, or the number that is defined by I squared equals -1. Now z star, the complex conjugate of z, is, if you remember, you just flip I to -I, so you get a minus bi. The next one we have is that z times z star, complex number times its complex conjugate, gives you the absolute value squared of that number. And we'll talk about the absolute value of a complex number in 1 second. The thing you notice here, though, is z times z star is the same as z star times z, which is a squared plus b squared. And you can see that by, if we just drew out the complex plane here, where we have the real axis here and the imaginary axis, and we have some complex number a plus bi would be right there. The absolute value of that complex number would be, it's sort of like its length or its distance from 0. It's generally how the absolute value is defined. And in that case, you can just use Pythagorean theorem. You know, this side is a on the real axis, and this is b I on the imaginary axis. And if we're looking just at the lengths, right, the length of this is b, length of this is a, and so the length of this line, the distance from that number and 0, is a squared plus b squared. So that is the square root of a squared plus b squared. So its absolute value squared would be a squared plus b squared. Okay, the next thing you can see, really just by using that equation, it's pretty easy to see the absolute value of a complex number z is the same as the absolute value of its complex conjugate z star. If we have 2 complex numbers y and z, you multiply them and then take the complex conjugate. That's the same as multiplying their complex conjugate. So yz parentheses star is equal to y star times z star. Another way of saying that is the complex conjugate of a product is the product of the complex conjugate. Similarly, the sum, or the complex conjugate of a sum, is the sum of complex conjugates. And lastly, if you take the complex conjugate and then you take the complex conjugate again, you get back to your original complex number. That's what this z star and then star equals z. Okay, so now that we have that, I'd just like to sort of define our new notation here, where we've got the psi vector is, and this is in yellow over here, is equal to c1 times the basis vector, the unit vector phi1, plus c2 times phi2. And these are showing phi1 and phi2 are unit vectors where phi1 has some observable quantity. There's some observable quantity, capital Q, and phi1 has a definite value of that being little q1, and phi2 has a definite value of that being little q2. So you could do that with like white and black, or hard and soft, any 2 quantities that are related in that way, where it's sort of either one or the other if you measure it. Okay, so now we have to look at what happens if we allow not only just c1 and c2, but also those basis vectors. Everything can be a complex number. And even if you don't quite understand why we may need complex numbers right now, you have to take my word for it. We do need complex numbers in order to do quantum mechanics successfully. And it turns out we will find out later, as we go on in quantum mechanics, we'll find out exactly how crucial quantum or complex numbers are, especially when we get to section 5. We will definitely see the absolute necessity of complex numbers in quantum mechanics. But for right now, you just sort of have to bear with me that they are very important. Okay, so the next thing is looking at what is the magnitude of a complex vector, right? So we know if we have like a normal vector, right, the magnitude, if I've got like some, A times I hat, this is I hat, the x direction unit vector, not the imaginary number, hopefully I'm distinguishing them enough, plus B times j hat, right, if this is a vector, the magnitude of the vector, really saying the magnitude squared, is going to be a squared plus b squared, which, as you can also see, this is the vector dot product with itself. So what happens if we have a complex vector? Now, right here, this is, for right now, this is the this is the x-axis and the y-axis, not the real and imaginary. If I have some vector that goes to this point right here, I want to know what the magnitude of this vector is. Well, there's some, it's got two components. It has A over here and B over here. Now this is where hopefully you can bear with me for this part, because it's a little bit not super intuitive. What we're really doing here when we're taking the magnitude of this vector is we are doing the length on this x-axis side squared plus the length on this y-axis side squared. Now it turns out the length squared is just a squared, right? Even if it's negative, it's just the square, because then it's positive. But not necessarily with complex numbers. In fact, we know sort of what the length of a complex number is. It's its absolute value, right? So this length over here, A can be sort of, you'd kind of need a four-dimensional graph in order to do like a two-dimensional complex vector. So we kind of have to use our imagination here. But this length over here, A can be a complex number, but the length of that side of this triangle, if we're making this triangle, the length of this side of the triangle is the absolute value of A. It's the distance from 0 to A. We kind of saw that, how that's the length of a complex number. And similarly, this side, the length of this side is the absolute value of B. So it would look like if we did the magnitude squared, just want to erase this part. Okay, if we did the magnitude squared, it would be this length squared plus this length squared. So it would be A norm squared plus B norm squared. Right? You have to take the norm squared, the absolute value squared, in order to get that length. Right? And that way, our magnitude squared, or even our magnitude when we take the square root, that will be a real number, and positive, which a length needs to be real and positive. So hopefully that would make sense. This is how we express the magnitude of a complex vector. So let's sort of see how this goes here. I'll use a very similar argument to what we did in the previous video. So, or actually I think it was 2 videos ago. So psi is expressed as C1. Actually, right now what I'm going to do, I'm going to do this actually in terms of color and hardness, just so we can sort of see this a little bit better. So we've got CW as a white unit vector, and now remember, all of these can be complex numbers now, plus CB as a black unit vector, which is equal to, you can also do it in the hardness basis, C soft, did soft first, soft unit vector plus C hard, it's the hard unit vector. Okay, and now we know that the magnitude squared of psi is equal to, well, it's the magnitude squared of a complex vector. These are unit vectors. It doesn't really matter if the unit vectors are real or complex. The magnitude squared is the sum of its components norm squared. So C white norm squared plus C black norm squared, right? But this is also equal to, right, if we do it in the other basis, C soft norm squared plus C hard norm squared. But the other thing we know is that the probability of being white plus the probability of being black is equal to the probability of being soft plus the probability of being hard, which is equal to 1. right? And so the only way that these equations are consistent is now if the probability is not just a square, which hopefully it shouldn't be, because the square of a complex number can still be like negative or even complex still. So thankfully, that's not what the probability is. The probability, it turns out, is the norm squared, because that's the only way for these to be consistent, is the probability has to be proportional to the absolute value squared of the component. And again, to make things easier on us, we'll have that proportionality factor just be 1. So probability of an electron being white would be C white norm squared. Probability of being black would be C black norm squared. And as always, we have normalization, which would say that psi norm squared equals 1. That would be our normalization. Okay, so the last thing I want to do in this video is talk about the dot product and how we can extend that into the complex numbers. Because if we look at what we really want this dot product to do, right, we want it to give us C1. This was the nice thing that we were able to get if we did phi1 dotted on psi. And the only way that works is if we have two parallel vectors. If the dot product of two parallel vectors is going to give us 1, and the dot product of two perpendicular vectors is going to give us 0. And it turns out this dot product, we actually have to do something slightly different. So what I'm going to kind of state what we need to do, and then I'm going to at least show a few examples of why this is what we actually need to do. So when we're doing the dot product, instead of just taking the dot product, we actually have to take the complex conjugate of the first vector, which would just be taking the complex conjugate of all the components and taking the complex conjugate of the unit vectors. Right, but in this case, it's just the unit vector that we're taking the complex conjugate of. But I'll show you sort of what taking the complex conjugate of a vector looks like here. So I'm going to erase this stuff up here. Hopefully you have it written down. And I'm going to, let's deal with two vectors here. And I will, I'll write them in the notation with I hat and j hat, which is still, in terms of just any arbitrary vector in 2 dimensions, still fully general, because you can just have, the x component be complex, the y component be complex. And so let's do that here. We've got this is the x-axis, this is the y-axis, and I have two vectors here. We'll call them v1 and v2. v1 will be I hat plus I, the imaginary number, times j hat. Okay, and v2 will be I hat minus I times j hat. Okay, and now let's plot these vectors. Now, it turns out, just because of how I set this up, the y-axis is going to be fully imaginary. So we could even write this as the y times I axis. This is not necessarily true. It's easier to show visually, because if you have, the x-axis being or the x component being able to be both real and imaginary to be complex, in like full generality, we would need a 3-dimensional or a 4-dimensional graph. So I'm just trying to show this a little bit easier. But v1 would look something like this, where we've got here, this is 1, and this is I. And then v2, it's like I actually drew this slightly off. I really wanted to have the y-axis extending down. v2 would look something like this, where this is 1 and this is negative I. Okay, and hopefully you can see, kind of by sort of the symmetry of the situation, this would look like a 45-degree angle, and so these are actually perpendicular vectors, which is why I chose these two specific vectors. And now the two things that we really want this dot product to do for us is we want it, if we put in like the same vector, right, parallel vectors, but really the same vector, we want to get its magnitude squared. And if we put two perpendicular vectors, we want to get we want to get 0. So let's start this with v1 star, right? We have to take the complex conjugate of the first vector dotted on v1. And if we do this, that's, well, if we just, you know, do the component method, that's 1 times 1, or that's 1 times 1. Actually, let's write it out this way. So this is we'll just write it fully out here. So v1 star would be I hat minus I j hat, because we have to flip the I, and then this would be dot product, the dot product with I hat plus I j hat, right? And so you know there's a 1 here. So this is 1 I hat, right? And if you just know, we know how the dot product works here. We take, you know, 1 times 1 and negative I times I. And 1 times 1 is, so this is 1 times 1 plus negative I times I. 1 times 1 is 1. Negative I times I, hopefully you know, is 1. So this is 1 plus 1, which is 2. And the magnitude squared of this vector, if you calculate it out, this would be the magnitude of 1 norm squared, which is 1, plus the magnitude of I norm squared, which is 1. So this is v1 norm squared, magnitude squared. Perfect. Okay, so that's what we want the dot product to do. But there's another thing we want it to do. We want, say if I took v2 dotted with v1, or v1 dotted with v2, right, but taking the complex conjugate, we want that to give us 0, because we can tell that these vectors are perpendicular. So let's see how that works. Well, again, we know that v1 star is 1 times I hat minus I times j hat, and v2 is 1 times I hat minus I times j hat. Hopefully you can see this, it kind of cut out. Okay, and now we can do the dot product here. This is 1 times 1 plus negative I with I, I'll rewrite that, plus negative I times negative I, right? But negative I times negative I is negative 1, right? That's just negative 1 times I times I, so negative 1, and that's, so 1 minus 1, which is 0, and they're perpendicular. So perfect. This is giving us exactly what we want. It's giving making perpendicular vectors the dot product, if we take the complex conjugate of the first one, 0, and for this other one, and if we have them be the same vector, it gives us the magnitude squared. So that's good. That's what we want this dot product to be. So now if we go here under our sort of new logic with our new dot product, it would look like phi1 star dotted on psi would be, well, if we look here, that's c1 times phi1 star dotted on phi1, which is going to be 1 if it's a unit vector, even if it's complex, because that's its magnitude squared, plus c2 times phi1 star dotted on phi2, but these are perpendicular, and so this dot product is going to give us 0. So we're left with c1. And so now our more generalized probability postulate for complex numbers looks something like this. From our other video. Okay, so let phi be the state with the definite value of some observable q being little q. If a particle is in the state psi, then the probability of getting that value little q is phi star dotted on psi, right? Because c sub q would be phi star dotted on psi, and then we take the norm squared of that. The norm squared of the coefficient gives us the probability. So this is our new and improved probability postulate for quantum mechanics.